targeted at providing support for as many different developer boards as it possibly can. And today I would like to tell you about a project that we started about a year ago, and we still in development, about our automatic testing laboratory for Linux distributions, not only Tyson Common, but others as well. And before we start, I would like to be honest with you, to warn you that it won't cover any new Python-based testing framework or some improvements in core libraries or in language itself. I would like to share with you how Python allowed us to fill in all the blanks that we had in our former workflow, and how it allowed us to be able to get rid of all the manual work during Linux releases that we had to do before inventing the automated laboratory. So I will start with a short introduction, and then I will share with you what drove us to create such a solution. I will describe all the elements of the testing laboratory. I will also share with you what's still on our to-do list, and I will end with a short summary. And to start with, this is how a single node of our testing laboratory looks like. As you can see, we've got a few groups of boards. They are in multiples, especially for redundancy. So if any test fails on a given target device, we can rerun it on the other one so that we know exactly that there were no hardware failure involved and that test fails due to some software malfunction. The boards in multiples also allow us to parallelize most of the work so that we can get as quickly as possible all the test results that we run in the laboratory. But I wish that our nodes looked this pretty most of the time. Unfortunately, once all gets hooked up and is in a fully operational state, it looks more like this. But let's get back to the pretty picture, and let me introduce you to what we've got on board. So on your left, we've got two mini board maxes. These single board computers serve us as target devices for x86 architectures. They can be used as both 64-bit and 32-bit target devices for Intel architectures, and switching it is as easy as replacing a UEFI on board. In the middle, we've got two Odroids U3+, which are the most common, most basic target device for Tizen Linux distribution, not only for our profile, but also for TVs, mobile, wearable, IVI, and so on. These are ARM-v7 based, and the next group is also ARM based, but in this case it's ARM64, and these boards are iKeys, the initial target device for Tizen Common on ARM64. Currently we're still investigating the possibility of replacing them with some better target devices. We're experimenting with Odroid C2s, Raspberry Pis, and Dragon boards. In the middle, we've got some supporting hardware as well, but these are not really interesting. These are just simple stock USB hubs. And the reason that we need so many USB connections are those boards on the top and on the bottom. These are micro SD card demultiplexers that we use for communicating with target devices and for having shared memory between target hosts and target devices. These boards are our custom design, and up close they look like this, or maybe some more like this. And since I'm completely honest with you today, it's not our first attempt at creating microSD card multiplexers. The board you can see up here is actually our second attempt, more successful one, that we use for about 9 months so far, with much success. And I will describe it in more detail in a minute, but first let me tell you what drove us to create all of this. And as you might be aware, or not, the change lifecycle in most of the Linux distributions, embedded as well, begins with a Git repository that stores all the projects that get onto the system images for target devices. And we use for code review Gerrit combined with Git. And for most developers, that's where their work starts and finishes. They push their changes, get them reviewed, and finally merged. For me and other release engineers for Tizen, this is actually where the journey of the new change actually begins. And it begins with activity of the package integrator. Package integrator creates a so-called submit request, which is a simple Git tag put into some specific object in Git repository, which then gets caught from the Gerrit event stream by our Jenkins server and is then passed through to the OBS, which stands for Open Build Service. Open Build Service provides us with the automatic rebuilds of all the packages that are passed to it. It creates RPM packages that we used to use, of course, in Tizen, in all of Tizen profiles. Not only it creates packages from the projects that are passed to it, it also rebuilds all the dependencies of those projects, so that we know that no regressions, no build failures are caused by the newly introduced change to the Git repository. Once all of it is already done, we get a new system image created by tools inherited from MIGO Linux distribution, especially MIG, which stands for MIG Image Creator, and that's where release engineers take the action. Once all of this, which is already automated, is done, release engineers make a decision whether a new change should be accepted or rejected. And that would be the automation of the whole process, together with the decision, will be our today's topic. As you might have already seen, the most basic tools for release engineers are the Open Build Service and Jenkins. And this duo works great. It is really stable. It has a wide community. It is pretty well documented. To be honest, one is better documented than the other. And it suits probably most of our needs. However, these tools are not really designed to work together, and the communication between them required some manual work from us. So, what it actually required from us? Well, once the OBS detected some build failure, release engineers had to investigate it and do some preliminary work to find out what might cause it. Second, similarly, we also have to check whether image introduces any regressions in comparison to the previous ones. And finally, once all of this is verified and we are sure that the new image will be better, greater in every way, we approve the inclusion of the change. Unfortunately, the whole process takes a lot of time. It requires to get all the software from the main Tizen.org repository, and then we have to flash all of the target devices that we currently support. So in a single node there are already 4 types of them, and these are not the only one that we test on. Then we had to flash them, run the test, get the results, and process them as well. As you might suspect, all these actions are pretty boring. They involved replaying over and over and over again the same set of activities. But still, it requires much focus, because the test results are pretty similar, and to differentiate one from the other, it requires a lot of focus, and it requires to be really observant person. So we asked ourselves, maybe we should test images less frequently. Maybe not all the changes that are pushed back to the main repositories require so thorough tests. We also thought that maybe just fewer tests would be sufficient. Maybe it would help us to make the whole process faster. And we also thought about the idea of the assumption. Maybe if the packages successfully are built, maybe we can assume that they will work properly as well. However, this is not how we do. We follow 3 basic principles. First of them, issues have to be resolved as quickly as possible once they are discovered. It is much harder to find a reason for all the failure if we check for them rarely, not as soon as they came up. Secondly, we always try to look for a proper solution, not just a simple workaround. Temporary solutions do backfire, and when there's a release process of the whole Linux distribution involved, they do backfire badly. And the final one, we do not publish any software that was never run on the actual target devices. Any developer who downloads software from Tizen.org servers is safe and can easily work with the software that has already been on an actual device and is verified that works. So the only way we could improve in this matter was to automate the whole process. And what task did it involve? All the tasks could actually be categorized in one of the few groups. So, first one, the easiest one, was the software. As I mentioned, OBS, although it works great and it provides us with all we need, it does not really inform about its state. So we had to create a poller for new images and to know when the new images were actually already available. We also had to provide a way of gathering all of them from the main Tizen.org servers. We also had to find a common way of controlling both hosts for tests and target devices. And also we wanted to share all the test results that we gather, so that anyone interested could reproduce them or check if there were no actual failures in what we did. The final one, the hardware category, was actually the hardest one. flashing target devices, so putting new system images onto them, was the hardest task, and that will be where the micro SD card multiplexers, or SDMaxes for short, will come into action. But let me start with the easiest one. As I already mentioned, Open Build Service does not provide any event mechanism out of the box. There are, however, some workarounds for it, some plugins for the OBS, but in the main installation, every user has to poll for changes manually. Also, it was designed for human interaction, so all the naming conventions are in a human readable state, and it requires some additional parsing so that it will be easily used in an automatic way. Also, new images are published in multiple locations, so doing it by hand was not really what we like the most about release engineering. And all those three tasks combined with our Jenkins server and some Python magic allowed us to automate all the work. So we've got currently a Python-based crawler, Python-based downloader bound to the Jenkins jobs, which are scheduled and queued on the testing server without hassle. As for the communication with devices, we considered multiple protocols. The first one that comes to mind is SSH, but it depends on other services like networking. It also depends on the connectivity provided by the board itself. Not all the boards that I showed you earlier are equipped with Ethernet port. Some of them, like Hikis, are wireless only, so it was not the way to go. We also considered serial console, which is the basic communication, which is the basic way of communication in the embedded world. However, it offers a low rate of data transfer, and it's not really flexible compared to the other protocols that we could use. So the default choice for the communication with devices is Smart Development Bridge, used in the whole Tizen development, which combines the best of the both worlds. It depends only on a single service that is already available on all of the Tizen images, Tizen system images. It provides us with shell, file transfer, and the data rates is decent. It's enough for our needs. As for the other infrastructure component, as for managing the configuration of the whole laboratory, we started with simple documentation stored in as a handbook using Sphinx, which I believe most of you are already familiar with. However, it was not enough for us. The pace of changes in the whole testing laboratory was too high to cope, to get both actual state and the documentation in sync. And that is why we also introduced some automatic configuration management tools in a separate Git repository called test.post. And for that we use the, I believe, most widely known Python-based tool for configuration management, and I don't mean the start stack. We store all the configuration management files as Ansible playbooks. That's how we get improved deployments. That's how we finally had updates on the testing laboratory automated. And that's how we get rid of the servers that were customly designed and that only an administrator of such a server knew how actually they were configured, so-called snowflakes. As for integrating with external infrastructure, we decided that all of the information that we got from our testing should be publicly available. We also wanted it to be easily available and with the possibility of future reuse if anyone would be interested in reproducing them. We also didn't want to introduce any new service to Tizen developers or community. That's why we decided to publish all of them on Tizen.org media wiki, which is provided with a handy tool, PyWikibot, that allows us to automatically edit and scrape information from the wiki pages as well. That's how we share the whole testing environment. That's how we publish all of the test results, and that's how we gather all of these information for future use. And finally, for the hardest part, we also had to came up with some unified way of putting new system images onto the target devices. However, the procedures that we formerly used were focused on manual user interaction. They were also mostly designed for just a single target device connected to the host, to the workstation of the developer. Also, all of these procedures were architecture specific, so it differed between Android, HiKey, Minoword, and any other target device that we or some other developers use. However, all of the target devices share a common feature. They can be booted up from a microSD card. That's why we came up with the microSD card demultiplexer, which can share the access of the memory between a host target and device under tests. We kept it as simple as possible. So on the board we've got a slot for board control. We've got, of course, memory card slot, connection from the board itself to the device under tests, and the same set of connections on the host side, and the power switch, which is a simple relay switch just to have the control over the power given to the board. And the simplest use case is to firstly connect everything to the host target, then put all the connectors to the target devices as well, switch the access of the memory card to the host server, flash it with a new system image, and then swap the access to the memory card from host server to target device, and with power switch power down. Of course, the board itself comes with a handy tool for automating the whole process, which allows us to have full control over the board and the device under test as well, with not only getting the information, but also having some preliminary tests. The current implementation is C1, but the Python one using libfttdi as well is in production as we speak. This way, we could move from our former workflow, which still involved some manual work, some release engineers interaction, to the fully automated process, just with Python tools and a piece of our customly designed hardware. And since it helped us so much with our work, but fear not, no one got fired because of the lack of work. We could finally move to some more interesting projects than repeating the same set of actions over and over again. We decided that all of this should be publicly available so that other workflows could be improved as well. I should note that we do not manufacture these devices, nor sell them. We only provide support if anyone would be interested in creating their own pieces of this open hardware. And that's why it's available to general public, it's freely downloadable, and we made sure that everyone who's interested can do that. So only open source software was used for the board design. Above you can see a KiCad in action, which was used to actually design the board. And of course, the link to the Git registry, which stores all the schematics for boards, connectors, and software as well. Currently, we've got some things on our to-do list still, and it's not only providing a Python way to have the control over the SDMaxes, but also creating some pre-test cases, so that bad images, the image system images that introduce some regressions, can be rejected as quickly as possible. We do expect some heavy load with Tizen 3.0 in production, and we would like to have images that will not be accepted out of the picture as soon as possible. We also require some more detailed way of monitoring differences between tested images, and still we would like to have some information from failed test runs as well. We also have in plans getting most of the resources that we got, so some load balancing is still in development but should be out soon, and the distribution of the whole system as well. We don't want to bind the whole process to a single location. We intend to provide the access to the boards for others as well. And to conclude all of this, I would like to share with you 3 lessons that we learned during the whole process of creating laboratory. First of all, in modern automation, there is absolutely no need to reinvent the wheel. All the building blocks for the automation are already there, and with the help of skilled developers like you are, in Python we can combine the mechanisms that were not designed to talk to each other. Also, creating custom hardware in the some rare events, although might seem a little intimidating, can greatly simplify tasks that are not easily overcome by software. Also, the whole automation process, although it costs a little at the beginning, pays off in the long term and allows to move to much more interesting projects in future. And that's all what I've got for you today. If you've got some questions, I will be more than happy to answer them.
Yes, we have 2 questions which works. What are the hardware requirements, transfer rates? Can I somehow emulate it?
Well, the Smart Development Bridge is not a piece of hardware, it's just a software. It's pretty similar to the other debug bridges or development bridges for most popular modern platforms. For us, it requires only a USB guest connection from the board side and a single daemon running on the target device itself.
Okay, thank you. And do you publish any report on Jenkins?
Well, our scripts and jobs and Python parts of the testing laboratory is available at git.python.org as well, in the same domain as the Max repository. So git.python.org /cgit/tools/tesla. That's where all of the source is stored. However, some parts are still under review, so they are not merged to the main Git branches yet. Some of them are still available only on the review.python